Okay, so this is our last class before spring break. This is sort of like the halfway mark of the semester. And the beginning of it, I'm going to continue with some product theory and try to get to a good place with it. But then in the second half, I wanted to kind of check in with everybody about some possible directions for the second half of the class. Okay, so in some product theory, last time we introduced some fundamental tools from additive combinatorics, the like Plunica inequality and Rusa inequality and so on. And the theme of today is like practicing using those inequalities. So let's call this Plunica Rusa Toolbox. All right. So these are all inequalities that connect sums and different combinations of sums and differences. So there is the Rusa triangle inequality. And it says that A times B minus C is bounded by A minus B times A minus C. Or if you can replace B and C by negative themselves, so you can say, you can also say this. Okay. And Plunica's inequality says that if A plus B is at most k times A, then B added to itself m times minus B added to itself n times is bounded by k to the m plus n times A. And the main lemma inside the proof of Plunica's inequality is also useful. It says that there exists, so that we have the same if, then there exists a subset in A, which sort of has the subset that has the additive structure that causes this to happen, so that for any set C, x plus C plus B is over x plus C is also at most k. Okay, cool. So one of our goals today is to practice using this toolbox. I was reflecting a little bit on where these come from. And I think a high-level point of view of where these come from is that if, say, this set is small, then there are a lot of coincidences where A1 plus B1 is the same as A2 plus B2. And by kind of rearranging those coincidences, you can see that there are also a lot of coincidences over there. That's the rough reason for these things. OK. Now, I made a small mistake last time, so I'm going to begin by correcting it. Thanks for the person who pointed it out to me. And correcting it is not a bad thing. It's already a good opportunity to practice these things. OK. So lemma 1 from last time was stated not quite right. It should have said if A is in Z mod P. So this is, let's call this corrections. Then either A minus A over A minus A is everything, or some kind of big mess with a lot of addition and multiplication and subtraction of A's is a lot bigger than A. OK, but the big mess actually should look like this. So you have A times A. You add that to itself a bunch of times. You also subtract that from itself a bunch of times. This is what we had last time. But I also need to divide by A minus A, which I left out last time. OK, So the second possibility is if you make this giant mess, it's significantly bigger than A. Okay. The proof of this is very clean. So the point is that if A minus A over A minus A is not everything, then you can find some B in A minus A over A minus A so that B plus 1 is not in A minus A over A minus A. OK. And then we can say that A squared is at most A plus BA. Because if you had any coincidences in that sum, it would cause B to be written, B plus 1. If we had any coincidences in this sum, you could solve for B plus 1, and you would be able to write it in this way. OK, but B by hypothesis can be written this way. So now we have A plus A minus A over A minus A plus 1 times A. This is less than or equal to the size of this thing. OK, and then now you just expand out this thing. And if you just expand it out, you get this. Now, what I did wrong before is I said we can sort of multiply by A minus A and move it. That's not right. I just want to do something very simple. This is a set of A1 plus A2 minus A3 over A4 minus A5 plus 1 times A6. Yeah. That's just what this means. And then take this thing and put it over a common denominator and expand it out. And all those things you can write this way. OK. It's always good not to trust me too much, but does it look OK to people? OK. All right. Cool. So then I had a lemma 2 from last time, which was true, but because it depended on lemma 1, I'm going to have to make it a little bit weaker. And it says that if A is in ZP, and the size of A is P to the S, 0 less than S less than 1, then can have A cubed minus A cubed should be at least P to the S plus a little bit. So last time we had A squared minus A squared, but that was based on having this nicer thing over here. OK. The proof of this is an excellent example of practicing using Plonica and Roos's inequalities. And what we're going to do is we're going to suppose that this is not true, so this thing is quite small. And then we'll keep using Plonica and Roos, and we'll see like many other things are small. And eventually we'll see that this thing is small, and this thing is small, and which is impossible by lemma 1. OK. So let's start with a remark. All right, so that we have that messy thing, A squared plus 3 minus A squared plus 3. Let's call this B, and A minus A, we'll call it C. And so lemma 1 tells us that the size of B divided by C is at least P to the S plus a little bit. Why? This B over C, it contains just A minus A over A minus A. So one possibility is it has the full size P, and then that would be good. That's a little bigger than P to the S. And the other possibility is that it's at least A squared, so then it's at least P to the 2S. And again, that's good. OK. So this guy is actually pretty big. And we're going to say if we suppose that this is small, then more and more things will be small, and eventually this will be small and have a contradiction. OK, so we'll do a proof by contradiction. All right, let me just say a cubed minus a cubed is less than k times a. And we're going to try to prove that k is big. All right, so this has a couple of easy corollaries. One is that a cubed itself is bounded by k times a. And another thing is that a cubed minus a cubed is bounded by k times a cubed. OK. So I can now plug this one into Plumika's inequality. Into Plumika's inequality. Once this one difference is small, then I could add up many copies of a cubed, and that would be also small. So Plumika's inequality says that I can take a cubed to one big power minus a cubed to some other big power, and that will be bounded by k to the m plus n times a cubed. But a cubed by hypothesis is basically a, so this is k to the m plus n plus 1. Okay. So all of these guys are small. OK. Now, what about, that covers b. So b is certainly small. But we need to think about b divided by c. So b divided by c is not quite obvious how it fits in here. But if you take b and you multiply it by c, then you'll get a sum of degree 3 things, which will be part of this. So that tells us that b times c is small. And b times c and b divided by c are related to each other. We can also say that a times b and a times c, these will also be small. OK. So then we can use Rousseau's inequality to relate b divided by c to these guys. And so we could say a times b divided by c is smaller than a times b, a times c. So this is the multiplicative version of the Rousseau inequality version 2. So subtraction has been replaced by division, and addition has been replaced by multiplication. OK, and then this is bounded by k to the order of 1 times a squared. You can cancel the a's, and we get that. So b over c on the one hand is big, p to the s plus gamma. It's bounded by b over c. But on the other hand, it's small. And if you compare these, you see that k needs to be at least a small power of p. OK. And then our third lemma was that if you take a subset A, and it starts off maybe small, p to the s, and you'd like to take products and stuff, and you'd like to get up to something much bigger, some p to the t, then you can do that with a controlled number of additions and multiplications. OK, so here's what it says. So the definition, poly k of A is A, take a product of k things, take a sum of k of those, and you can also subtract similar stuff. And then lemma 3 says if 0 is less than s is less than t is less than 1, then there exists some k that only depends on s and t, so that if A is a subset of fp of size p to the s, then the size of poly k of A is at least p to the t. So I sort of, if you start with a set A and you're allowed to add and multiply, then in a controlled amount of time, you can spread out to cover a very large chunk of FP. OK, and the proof of this is just repeat lemma 2 many times. All right, so this is sort of where we left off last time with this mistake about the denominators corrected. OK. Yeah. So a takeaway that I have from the Ruza and Plunika's inequality is that there's some kind of contagiousness of structure. So if you see that one projection or a few projections are very small, then it implies that some other projections are small. Or if a few subsets are small, it implies that other subsets are small. So yeah. OK. So let me spell that out. Contagious structure. OK. So contagious structure lemma 1 says that, so Z is, so in all of these things, maybe I should say, these are theorems that work in any abelian group. So Z is an abelian group. And they have, some of them have versions in non-abelian groups too that are not that different, although we won't talk about that today. But, OK. And we have some subsets of this group. OK. So same setting. So Z is an abelian group. All right. So suppose that A plus T1 times A is not too much bigger than A. And also A plus T2 times A is not that much bigger than A. And remember that these are, so this kind of thing is basic in some additive combinatorics, some product theory, but it also looks like a projection. We're taking the product set A cross A and we're projecting it in the T2 direction. OK. So if we have these two small projections, then if I project in the direction T1 plus T2, it's also small. Pretty small. Actually, let's do T1 times T2 first, because that's easier. And this will be a nicer number. I think it's 2. All right, so there's the proof. All right. OK. So this is actually, let me also make all of these. Yeah, let's also make all of these minus signs. OK. So A minus T1A is quite small, and A minus T2A is quite small. I'm going to multiply this just by a constant T1. So this here, it implies that T1A minus T1 T2A is quite small. OK. Ruza had a funny idea that sort of think of the size of this as some kind of distance between A and T1A. So A is kind of close to T1A, and also T1A is kind of close to T1, T2A. And so something like the triangle inequality would tell us that A is close to T1, T2A. And you can really use the Ruza triangle inequality in this way. OK, so the proof is by Ruza triangle inequality. So we have to decide who's A and who's B and who's C. And we want B minus C. We're going to try to bound B minus C. So this is going to be B minus C. I'll call it B bar is A. C bar is T1, T2A. And then A bar, I guess, must be T1A. OK, so then the inequality says T1A times A minus T1, T2A is bounded by A bar minus B bar, so T1A minus A, times A bar minus C bar, T1A minus T1, T2A. OK, so A times A minus T1, T2A is bounded by these guys that are both small, K squared, A squared, and then that's it. I just divide by A. OK. So if the projection in the negative T1 direction and negative T2 directions are small, then same for the negative T1 times T2 direction. That's also small. All right. All right. Contagious structure lemma 2. You can replace T by minus T. So if A plus TA is less than or equal to KA, then A minus TA is less than or equal to KA. Yeah. So we saw this last time that if a sum set is big, then the different set should also be, if a sum set is small, then the different set should also be pretty small, and vice versa. Yeah. OK, so proof. This is also so this is going to be a Plunica inequality proof. So let's say that TA is B. So A plus B is pretty small, and then therefore we get that B minus B OK, let's try Ruza's inequality. So I'll say this is B and this is C, because I want to have that B minus C on the right-hand side. And then and A, I guess, can be A. A minus TA is less than or equal to. And then let's use the second version. A plus TA. So this one we know is small. Now we need to check that this one is small. But by Plunica's inequality, starting here, a plus a is less than a squared a. So this is less than k cubed a squared. Okay. And now the most interesting and difficult of the contagious structure lemmas says that if a plus ta is small, a plus t1a is small, and a plus t2a is small, then a plus t1 plus t2a is small. This is the trickiest, so I ended up needing the largest exponent. Okay. All right, so this is a very good exercise in combining these things. We're going to start with this, and we're going to relate it to some sets that sound even much bigger. But then those sets we can easily chop through with these inequalities and get back to A. OK, so A plus T1 plus T2A. I'm going to bound that, and this looks quite wasteful, by A plus T1A plus T2A. So this is quite wasteful because I'm allowed to have T1 times one guy plus T2 times the other guy. Here I only had T1 plus T2 times the same guy. But it's a true inequality. OK. And it's helpful because we know something about adding T1a to somebody. And actually, the nicest thing we know about adding T1a comes from the main lemma. So here in the main lemma, we could have this b could be T1a. And then we'll have a very general thing about when you add b to somebody of this form, and it doesn't get very much bigger. So we'll have the main lemma. And it tells us that there is some set x1 in A, so that for every c, x1 plus c plus t1a is bounded by k times x1 plus c. Whenever you see a sum like this, you can remove this plus t1a, and it only slightly increases the size of the set. Or you can, yeah. OK. And same for x2. OK. OK, so now we want to bound this thing. And we could get rid of the T1a and get rid of the T2a by using this inequality if the rest of the stuff had the form x1 plus somebody or x2 plus somebody. We don't have an x1 plus somebody here or an x2 plus somebody in here. So I'm just going to add them in, which again sounds extremely wasteful, but is actually OK. So A plus T1a plus T2a, that is bounded by x1 plus x2 plus a plus T1a plus T2a. All right, so now this has the form x1 plus some stuff plus T1a. And I can get rid of the T1a by main lemma 1. So that's less than x1, less than, I pick up a factor of k. x1 plus x2 plus a plus t2a. And then this thing has x2 plus some stuff plus t2a. So I can get rid of the t2a by main lemma 1 again. So this is less than k squared x1 plus x2 plus a. Now, x1 and x2 are subsets of a. So this is less than k squared a plus a. And then by Plunika's inequality, this is less than k to the fifth. Yeah.
Wouldn't you need that a plus a is less than ka, but you can only get k squared a from the a plus t1a event?
So starting from here and applying Plunica, I can say, if you call this guy b, that b cubed is smaller, b plus b plus b is bounded by k cubed a. And b plus b plus b is the same as, yeah. 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 It wouldn't really matter if this was a bigger number, but okay. Cool. Cool. Okay, so qualitatively, we have this picture that the small projections are organized. They have algebraic structure. You can add two small projections. You can take the negative of one of them. You can multiply them. So they are a ring. It's not so clear that one is in there, but anyway, they have a lot of algebraic structure. And that mesh is something that we saw in examples. You know, we wrote down, like, here's an interesting set that has a lot of small projections on the first day. The interesting set was an integer grid, so integer cross integer. And the set of directions were rational numbers with small numerators and denominators. And you know, if you add two rational numbers, you get another rational number. If you multiply two rational numbers, you get another rational number. And the numerology here is roughly, maybe not precisely, but roughly consistent with that. So if you took rational numbers with very small numerators and denominators, you get really great projections. Then if you add two of them, you get a new guy where the numerator and denominator are bigger. And that is still a pretty good projection, even though it's not quite as great as what you started with. And that's what we see here. So this guy is a pretty good projection, although not quite as great as what we started with. And same with addition. OK, so that structural feature of our first example, it was not just a coincidence about that example. It's a general thing. And it follows from these inequalities. OK. OK, great. So now with this toolbox, we're going to start to make progress towards the bourgain-katz-tao projection theorem. And we will prove an important inequality of some product theorem. Okay. So there is a theorem. So if A is a subset of Fp, and it has a certain size, p to the SA, and D is a set of directions in Fp, and D is p to the SD. Let's say that each of these is strictly between 0 and 1. Then there exists some epsilon, depends on the s's, bigger than 0. So that the following thing is true. The maximum T in D of A plus TA is significantly bigger than A. So let's make some remarks about it. So here's an easy corollary. If you just take a plus a times a, that should be bigger than a. Why? Well, let a be d and plug it in. But this theorem is stronger than this corollary in two important ways. One point is that we're not taking the union over d of all these sets. We're just taking the maximum over d of all these sets, which a priori is a much smaller thing. And the other point is that the set of directions is independent from a. So the most interesting case here is when SD is much smaller than SA. So we have a medium-sized set, A, but we consider only quite few different projections. And still, that's enough that one of those projections will cause the projection to get bigger. OK. We're going to use one of our tools from, this is SA. We're going to use one of our tools from day one of projection theory, which was the double counting. So at the beginning of projection theory, we proved that if x is in FP2 and d is in FP, then the maximum over t and d of pi t of x is at least the minimum of the size of x and the size of d. OK. So if it was the case that SD was bigger than SA, then this double counting implies our theorem. Because then this maximum would be at least either p to the 2SA, which is the size of our x, or p to the SD, which is the size of d. OK. By itself, that is worth noticing, but by itself, it's not that exciting. The hard case of our theorem is when SD is far smaller than SA, although it has to be positive. All right. So here's the proof of our theorem. It combines the ideas that we've seen today. So first of all, even though d itself is small, if I'm allowed to add and multiply elements of d, then I can make that as big as I like. So the first step is by lemma 3, there exists some k, which depends on SA and SD, so that poly k of d is significantly bigger than p to the SA. And therefore, by our double counting argument, there is a u in poly k of d, so that a plus ua is significantly bigger than a. So we don't yet have a u that's actually in d, but we have a u that is formed by doing a bounded number of multiplications and additions and so on of things in d. And we play this against the contagious structure. So, but if the maximum t in d of a plus ta was less than ka, And we can use contagious structure many times. And we'll see that also this guy should be small. So then use our contagious structure, and we get that the maximum u in poly k of d of a plus ua is smaller than k to a power here. And so this power depends on little k. But then if you unwind, little k depends on SA and SD. Right. So if all of these projections had been really small, then other projections would be small where you add or take negatives or multiply, and you would get, by putting that together, you would get that these are small. Okay, and so the conclusion is that k to the c is bigger than p to the gamma, and so k is bigger than p to the gamma over c, which is our p to the epsilon. That's the proof. Okay, so let me restate the projection theorem that was sort of this, that we announced on Tuesday as our next big goal, and we'll compare it to this theorem, and we'll see that it's closely related, but there's still something that we need to do. Okay, so our goal, which we won't get to today, but soon, is a theorem BKT that if x contained in fp squared, and so x could be p to the sx, where sx is really between 0 and 2, and d is contained in fp. The size of d is p to the sd, where sd is bigger than 0. Then the maximum of the projections is bigger than the square root of x. So the maximum t and d of projection t of x is at least p to the epsilon x to the 1/2. Okay, so this theorem, although the epsilon is small, is important because it's the first theorem in projection theory that fundamentally distinguishes the prime fields from not prime fields. And that is important in many applications, and it gets kind of bootstrapped in the strong theorems, that recent strong theorems, like K conjecture, Furstenberg conjecture, and stuff like that. Okay, so let's compare this goal to what we have from some product theory. They look almost the same if you just set x equal to A cross A. So let's call this theorem 1. So theorem 1 is equal to theorem BKT in the special case that x is a product set, A cross A. Yeah. Any questions or comments? Okay. So maybe it's worth reflecting, since this was our main goal. Why in the proof of theorem 1 did we need to know that x was a product set? So the proof of theorem 1 is over here. It's not very long. this double counting argument has nothing to do with product sets. And we start to go along. We can say that the direction itself might be very small, but if we take polynomials in the direction set, then we get something big. So up to here, we have not used at all that our set is a product set. This would have worked for any x. And then we use the contagious structure. So the contagious structure said that if all of these guys were small, then also the projections in directions t+1, t1 plus t2, and so on are also small. That contagious structure step did use the fact that this had this particular form, which allowed us to think about everything in terms of Roos's inequality and the Plunica inequality and so on. Right. So I have been asking myself if it is possible to prove those contagious structure things directly for arbitrary sets. I believe that they're true, and it sort of follows. So the proof of this theorem is going to be some kind of reduction to the case of product sets. So I think that in hindsight, the contagious structure is true in general. And so I don't know, it seems like perhaps it would be natural that it could be proven in general, but I'm not sure. OK. Now, on the other hand, I would like to argue that, OK, so then at first you see this and you say, well, product sets are extremely special subclass of all sets, so this is not very good. But I would like to try to argue that if x if this thing is small at all, then x is quite close to a product set. And if I convince you of that, then maybe you'll feel like what we've done so far is actually pretty close to our goal. All right. So let's talk about that. All right. So remember that pi t of x1, x2 is x1 plus t, x2. And also pi infinity of x1, x2 is simply x2. It's just a convention. OK. Now we have some set of directions. And by performing a change of variables, we can assume that two of the directions are 0 and infinity. So without loss of generality, the direction d is 0 and infinity, and then some other directions. OK. Right. So now x is, any set x is contained in pi 0 of x cross pi infinity of x. So pi 0 of x are all the possible first coordinates of anybody in x. Pi infinity of x is all the possible second coordinates of everybody in x. And so this product contains x. So this is true for any set. But because these are directions in our direction set, so let's suppose that the maximum t and d of the size of pi t of x is at most k times the square root of x. And imagine that k is pretty small. OK, so in that case, the size of pi 0x cross pi infinity x, that's the size of pi 0x times the size of pi infinity x. That's at most k squared times the size of x. So this here is an actual product set. X is sitting inside of it. And x is, occupies a large fraction of it, if this is a scenario that we're worried about. OK, so in order to prove this theorem, it suffices to prove it for sets that are a large fraction of a product set. And on the other hand, we've just proven it for actual product sets. OK, so now maybe it feels like this theorem is in reach, that we just have to, all we have to do is to take our proof that works for honest product sets, and we have to extend it to something that is a large fraction of a product set. Cool. So we'll do that after the break. It does involve some significant ideas. And there's significant recurring ideas in additive combinatorics and projection theory and lots of stuff. And there are ideas about going back and forth between something that is true a large fraction of the time and something that's true all the time. OK, so that's the part of the class today about sum product theory. Take a minute and see if you have any questions or comments, and then we'll let that rest for the break. Yeah.
So is it like in the proof theory that we have our freedom to choose like gamma?
Yeah, that's right. We have freedom to choose gamma. So lemma 3 lets us put here any exponent t that we like, and then this k will depend on t. So this gamma can be pretty big. We could be halfway from SA to 1.
And the C there depends on gamma, right? Like in the last line, it's like sort of like absolute equal to gamma over C. In the last line.
Yeah, so this C, yeah, I mean, we could make it, maybe it's helpful to say gamma is 1 minus SA over 2. So yes, things depend on gamma, but gamma just depends on SA. So things still only depend on SA and ST.
Okay. Would there be a like good gamma that gives us a nice bump for the epsilon there?
Yeah, so another thing you might wonder about is you might want to write down the actual size of epsilon. And you might like to adjust the parameters in our argument strategically to make it as big as possible. So you can do that. The actual size of epsilon there's a formula for it, but it is pretty small, and so people often don't write it down that carefully. Adjusting gamma, I think something like this is reasonable. It's not going to help a whole lot. Yeah. Yes?
What is kind of the complication if you just kind of try and sort of straightforwardly plug this into theorem 1? You can say that this will be kind of less than, I guess you can take pi 0 of x union of pi infinity of x as A, and then apply to theorem 1, which seems like it would contradict kind of the statement that the projections are all less than the square root of x. Or am I missing something kind of more subtle there?
Yeah, OK. So what happens now if we try to directly deduce our goal theorem from theorem 1? So let's say A is defined to be pi 0 of x union pi infinity of x. And so x is indeed a subset of A cross A. And the size of A is still basically this. OK, so now theorem 1 tells us that the maximum t in D of the size of pi t of A cross A is big. OK, now we actually want to bound the size of pi t of x. How are these related to each other? Well, this is a subset of this, so we know this. But that's the wrong direction for this to be helpful. So we're worried about the following scenario, that x, so A cross A is a product. So there's A cross A. And inside of it is x, which is a pretty big fraction of it. That's x. And then somehow we managed to find a projection where the projection of x is quite small, even though the projection of A cross A So we know the projection of A cross A is large, but maybe there's a significant piece that got projected onto something small. That's what we don't know yet. Okay. So your next homework assignment is due the week after the break, and it's not a regular problem set with problems. It is a check-in and reflection about the class. So you'll ask people to reflect on what we've learned so far, see what parts seem confusing or what parts seem like clear, and then to think about what direction we'd like to go in the second half of the class. So there are a bunch of topics that I think are cool that we could talk about, and we could talk about just one or two of them in depth. We could do all of them in less depth, and I wanted to get your thoughts about it. So I'm going to remind people what the topics are and introduce some of them that I haven't properly introduced before, so for context. Okay. Okay, so these are topics that are connected to, maybe applications of, maybe extensions of the stuff in projection theory that we have learned. Okay, so one topic is mixing or random walks on discrete groups. Some of the key names are bourgain-katz-tao. Another topic is a part of homogeneous dynamics. And it's also about mixing. It's like mixing of orbits. And some of the names involved in it are Guth, Danny, Ratner. And there's some recent work of Linden, Strauss, and Mohammadi. Okay. There is Furstenberg, which is like the sharp projection theory estimate in 2 dimensions. And another thing that's related to this is the Kakea problem. And there's a recent proof of the Kakea conjecture. Monday after break, a colloquium, Hong Wang is going to come and talk about the Kakea conjecture. Okay. So I wanted to tell you a little bit about some of these things, and just so you can be a little informed as you think about what you'd like to study. Okay. So this one I tried to mention on the first day, but I don't think we really talked about it at all. But I wanted to say something about it. So the word homogeneous is a reference to homogeneous spaces. And a typical example of a homogeneous space is SLNR modulo SLNZ. I'll call this X. It's homogeneous in the sense that SLNR acts on this space on the left, and the action is transitive, so every point gets mapped to every other point. Why would you care about this space? So you can think of X as the space of lattices in Rn with covolume 1. Why? So start with the unit cube lattice. I can make another lattice of covolume 1 by applying an element of SLNR to my lattice. Now, not all of those will be different. So if my element was in SLN Z, it will map the lattice Z to the n to itself. So that's the kernel of this map. And so the space of lattices is the quotient, like this. OK. So that's a homogeneous space. What are homogeneous dynamics? So SLN R acts on X, and it acts transitively. So if you take any x and x, the orbit SLN R of x is the whole space. However, SLN R has many interesting subgroups, and you could take one of those subgroups and look at that orbit, and then different things can happen. So let's say H is a subgroup of SLN R, and you look at H times x. So that's some kind of visual. So this space is almost a manifold, and it has finite volume, and it has a little cusp, which is sometimes important, sometimes not important. And we have a point little x in here, and we take this orbit, which wraps around this thing in a sort of crazy way. It sort of looks like this. And people would like to know, is this kind of evenly distributed on the whole space, or does it concentrate somewhere? And if so, where might it concentrate? So how is the orbit distributed? OK, so questions of this type come up in many places. Let me mention one of them to you. So here is an application in number theory. It's called the Oppenheim conjecture. OK, so let's say Q of x1 up to xn is a quadratic form. And the question is to understand how Q behaves when you put in integers. So question, how is Q of z to the n distributed? OK. So one observation is that if Q is always positive for real numbers, then Q of z to the n will be always positive. And another observation is that if the coefficients of Q are all integers, then Q of z to the n will be integers. And those are the main obvious reasons why Q of z to the n would not be distributed evenly on the real numbers. So motivated by that, Oppenheim made this conjecture quite a while ago. So the conjecture was that if n is at least 3, and the signature of Q is mixed, so it's not always positive and not always negative, and the coefficients of Q are not contained in z times alpha for any alpha, then Q of z to the n should be dense. And also, in fact, not just dense, but kind of, his conjecture said it should be dense, but later people thought, if you take a big ball in z to the n and you apply Q to it, you should get a set of points that are quite evenly distributed along an interval in the real life. OK. OK. So this conjecture was proven by Margulis. And his proof involved connecting this problem to this setup of an orbit in the space of lattices. So how does the connection go? Well, the way I've written it right now, I have the standard lattice, Zn, and I have some obscure quadratic form. But I could make a change of variables so that Q is a standard quadratic form, and then I would have some obscure lattice. So after a change of variables, Q could be just x1 squared plus xk. Let's say we're just in 3 variables, and we have a mixed size. Q is just this. But Z3 becomes, maybe Q becomes this. Z3 becomes lambda, a new lattice. OK. OK. So now we have a lattice, which is one point in that space. And we don't know anything about it, really. It could be any point. But why would we have a whole orbit? Well, we have a whole orbit because this quadratic form has a lot of symmetries. So remark, the group SO21 sitting in SL3R, that preserves this. That's just the definition of this group, and a somewhat non-trivial fact is that this is a large group. It's not, it's not the identity. OK. And so you could use lambda, but you could also use any of these guys. So you could use the lattice lambda, but you could also change coordinates by anybody in SO21. So you get a lot of other lattices. And you can use any of these lattices. And it's equivalent to the original problem. OK, so now over here, this orbit H, this is going to be SO21. And n is going to be 3 in this particular application. And this initial point, little x, is going to be our lambda. And so we can use any lambda in this whole thing. OK. So now it matters, like, who is in this orbit. And if the orbit was dense, so then lambda is allowed to be basically any lattice. OK, and then once lambda could be basically any lattice, then maybe it's believable that that Q of lambda should behave in a nice way. Or on the other hand, maybe this orbit is quite a bit smaller, and there are only a few special lambdas in the orbit, and then it's not so clear what's going to happen. OK, so that is how this setup in homogeneous dynamics occurs in a natural way in this number theory application. And there are more applications also in a similar spirit. OK. Now, what does it have to do with projection theory? All right. So there are lots of different subgroups, H there. And this problem actually behaves in really different ways for different subgroups. And the subgroups where there are strong theorems are unipotent subgroups. Let me just write an example of a unipotent subgroup. So let's say we have SL and R, and our group H, but I'll call it U for unipotent, is the group that looks like this. Right, so you have all ones on the diagonal. You have one guy in the upper right-hand corner called T, which is not 1, and everything else is 0. So this is a subgroup. And this is one that has behaved particularly nicely for this problem. OK, what is nice about it? Let's also just, for example, we work with SL2R, so U is just this. OK, so what I'd like to do is I'd like to take, so let's say UT is 1T01. And so I'm in principle interested in the infinite orbit, but I'm sort of interested in the asymptotic behavior. So I want to study the set of U sub t of x, where t goes in some range. OK. So what's important about this structure is that it interplays very nicely with a different matrix. So suppose now that little a is the diagonal matrix. Little ar maybe is e to the r 0, e to the minus r. So that's in SL2R also. And the nifty thing about this is that little a r ut little a minus r is u e to the r t. Right. And so, right. So I can take utx, where t just goes from 0 to 1, and then I can apply a to it many times, and a inverse to it, a1, let's say, many times, and a1 inverse many times. And this thing is now, say we do this n times. That. So in other words, in order to study this thing, I start with that, which is quite innocent looking. So that's just like a nice segment that I can draw in my manifold. And then I do this operation of conjugating by a, and I keep conjugating by a, and eventually I get this thing. So to understand this thing, it's just important to understand what happens when we conjugate by a. Okay, so what happens when we conjugate by a? All right. All right, so the conjugation map, conjugation by a, it takes our homogeneous space to itself. But if you look at a little piece of the homogeneous space, take a little box here, then some of these directions will be stretched, and some of them will be contracted. So look at maybe something like this. Okay. And now, so let's say our orbit is yellow. So we've done this a few times, so we have some piece of orbit. And now we want to see what's going to happen to the orbit. Well, some piece of it got squashed. So, okay. So it depends upon this orbit, and then if two strands here are separated by a direction that's the squash direction, then they'll end up closer together here. And if they're in a direction separated by a direction that doesn't get squashed, then they'll stay far apart. So in this box, there is a direction. So this box is B, and there's a direction D sub B, so direction in B that gets contracted. It's not quite true, but it's almost like this box gets completely flattened. It's almost like the box is being projected to something lower dimensional projection. Okay. And these guys go through a bunch of boxes. So here's B2, B1, B2, and so on. And the direction dBj is changing. Right, so you can choose coordinates so that the direction of these orbits is a coordinate axis. And then the direction that's getting squashed is changing. So it's sort of like as you go along here, there are projections in different directions. OK. So let's call this conjugation map phi. So phi restricted to b is sort of like a projection, and changing b is sort of like looking at different projections. So we have one set of orbits, but they pass through a bunch of boxes, and so we're applying different projections to them. OK, so this is roughly how projection theory comes into understanding how these orbits look like, which has applications in different areas. OK. OK, so I guess I mostly talked about this one. But it was the one that we hadn't talked about, and I thought I should say something about it. I have just a couple minutes. Should we? It's almost spring break. Maybe we should take a break, or we should just stop early. Yeah, let's do that. So let's stop there. I wish you a very nice and restful and fun spring break, and I will see you afterwards.